I want to present to you Boscovich's unified field theory and its modern application. It's just to bring to your attention some people's work. So this, as far as I know, what I'm talking about is the first unified field theory, and this lecture is to be split into three parts. The first part is going to be a brief historical introduction to Boscovich's theory and my work on the translation. And the second part is to deal with Professor Dragoslav's work, who has extended Boscovich's theory to modern applications. And part 3 is going to be about August Krintz's work on the math of the unified force. So on my part of the work, I'm on sort of like trying to do translation. And Boscovich was dealing with physics in the 18th century. And what I'm trying to do is translate Boscovich's work from Latin into English. My latest book is entitled On Living Forces, and it was written by Boscovich in 1745. In it he says, et quintum, and so forth. This is all Latin, but you can recognise there that there is the word Newton, and so forth. So concentrating just on this last bit of the sentence, what it translates to is a proposition concluded from Newton, demonstrated, quantum physics allowed. And this was written in the 18th century, and what we can see there, he was talking about quantum physics in the 18th century. Quantum is a Latin word, however, it roughly translates its meaning as much as, so it might better be read as proposition concluded from Newton, demonstrated as much as physics allowed. So we have this problem in translation, and there are other issues as well, that Latin words have been adopted by the English language. So what Boscovich meant by quantum in the context of the 18th century does not now necessarily mean what we have adopted the word to mean. But Boscovich is still talking about quantum physics. So let's go on to the history of physics. From the theories of matter from early times, there was a question of what was matter made of. Was it continuous or discontinuous? The atomic theory of matter came from the ancient Greeks, such as Democritus. This is a sort of typical thing said by the Science Education online, which I'm quoting. 460 BC, Democritus from Greece developed the concept of dividing matter into smaller and smaller pieces until you could divide it no more. He called these smallest pieces atoms, from the Greek meaning indivisible. This was a philosophical idea rather than a scientifically based theory. So, after the Greek era, scientific investigation greatly diminished. The Romans, although great engineers, were less interested in the nature of matter, and with the onset of the Middle Ages, dogma became more important than science, by dogma demolition. For over 2,000 years, the atomic theory lay dormant. 1803, atomic theory started. This is according to what it was on the internet, online. John Dalton, an English chemist, divided the term the atom when he suggested that each element was made up of unique atoms, and the atoms of an element are all the same. He formulated his theory that chemical reactions result in the union and separation of these atoms. and that atoms have characteristic properties. Combinations of atoms bound to each other he designated as molecules. For a while, it seemed that the atoms were fundamental. As their name suggests, they could not be split into anything simpler. However, towards the end of the 19th century, it became clear that atoms are not fundamental. They themselves are made of smaller particles. One of these atomic particles is the electron, which you now think of as fundamental. And this is what I'm quoting from the internet. And that is wrong. It's on the internet and it's wrong. First of all, it misses out a lot between democracies and Dalton. So it is a very condensed history. Second, it is mixing up two different concepts by the word atom. What Dalton meant by atom is not what the ancient Greeks meant by atom. That might be one of the reasons for the confusion. The ancient Greek atom is the idea that it could not be split, but the Dalton atom could be split. So the ancient Greek atom has never been split and is close to the idea of what Boscovich was talking about in his atomic theory when he was talking about an atom as being a point particle. Now modern physics is based on the idea of the point particle. Hence, Boscovich is known as the father of atomic theory. Online, we have the person asking the question, who is the father of chemistry? By Anne-Marie Himmelstein. It is strange that my science education has omitted this out, as it probably has been omitted from your science education. But science education is a brief summary of some important parts of science, and they miss out a lot. So the educators could not have thought it important to mention Boscovich. And that is strange because modern physics comes from Boscovich's theory. The concept of a point particle may sound trivial, but the theory based on it is non-trivial. Quantum physics originated with Boscovich, and he dealt with relativity of Galileo. So what I'm proposing is he gave a unified theory of quantum and relativity physics. These are peculiarities which are not fully researched, such as Boscovich did deal with the idea of a universal speed, so maybe he came close to Einstein's relativity. The theory was published by Boscovich in 1758. This is the cover of the book, Theory of Natural Philosophy. Yale University Library says of the book, Dubrovnik, or Roger Boscovich, was a mathematician, physicist, astronomer, philosopher, diplomat and poet. And he was educated as a Jesuit in Rome. He became a professor of mathematics in 1740. After his studies, Boscovich joined the Jesuit order in 1736. He began publishing mathematical, physical and astronomy works, and to his death in 1787. His main theories were proposed in his book Theory of Philosophy Naturalis, first published in 1758, on the harmony, or in harmony with conclusions arrived at by the methods of modern scientific research 2 centuries later. He wrote about the constitution of matter, the law of gravitational forces, atoms, space and time, relativity, and the theory of light. His work anticipated modern theories of physics, and that is a quote from Yale University. So when I say a unified theory of quantum and relativity physics, I mean an 18th century version of this. Of course, with revolutions caused by Einstein, we are thinking in terms of a relativity theory and quantum theory that has so far refused to be combined into a unified theory. But in the 18th century, there was a unified theory. My position is that modern physics in the 20th and 21st century, with its quest for a unified theory has gone wrong, and the real unified theory was in the 18th century. What does not help with the modern quest for unified theory is the fact that the educators are teaching a bad version of history. So I've presented you what the history is. For instance, the history they tell you is they credit quantum theory starting in 1900 with Planck, and so they're completely trying to omit Boscovich. A European Space Agency website says, and I'm quoting, "At first this theory met resistance, but due to the successful work by Niels Bohr in 1913, calculating positions in spectral lines, using theory, it became generally accepted. The quantum theory was born." Planck himself said he had, despite having invented quantum theory, he did not understand it himself. Nevertheless, he received Nobel Prize for Physics in 1980. And so they are ignoring the dealing with quantum-type ideas before Planck. And this sort of thing is what we could call a distortion, what we call a weak history. They are presenting a history which is not completely accurate when they say that Planck started quantum theory. There's a biased retelling of history by modern physicists. They don't say what actually happened, and they instead they give a biased version. Quantum theory actually starts with Boscovich. When a child translated one of Boscovich's books, he says, "Boscovich's theory," I'm quoting him, "also suggests curious, almost uncanny imitations of general relativity and quantum mechanics." And that is quoting from a book published by MIT Press in 1966. So what is the point particle theory? Well, we get taught about the point particles, so we are treated like the idea is obvious, but that may be another reason why they miss out teaching who came up with the idea first. The educators think it's trivial, but it's non-trivial. Boscovich had a unified theory of point particles. It's not so obvious, that theory, because it deals with unified force. And it's the basis of theory comes from Newton's query 31. Newton's 31st query reads the following. Have not the small particle bodies certain powers, virtues, or forces by which they act at distance, not only upon the rays of light for reflecting, refracting, and inflecting them, and so forth. For nature is very consonant and comfortable to herself. Here, Newton suggests that many forces stronger than those already known to man, like gravity and magnetism, may exist. These strong attractive forces may explain how small particles interact with each other. Cassino, quote, says, "In fact, Boscovich borrowed from query 31 the idea of reducing to a single force single law of nature, the elementary interactions between his puncture being roughly translated as a point particle." And also, by the way, when I talk about Boscovich's theory unifying Galileo's relativity with quantum physics, that is basically what modern physics is, modern quantum mechanics is anyway. It's looking at an extension of what is Newtonian physics and not taking into account Einstein's relativity, and I then tried to combine Einstein's relativity. And so I published one article on it in 2001 in an alternative journal called Nexus. Now I'm getting on to part two. I'm not going to be able to adequately deal with this, so it's going to be very brief. So I'm mostly quoting Dragoslav Stoiljkovich. He graduated in 1971, finished a master's science degree in 1978 and a PhD in 1981 at the University of Belgrade. master's thesis and doctoral dissertations were devoted to the polymerization of ethylene at high pressure. From 1971 to 1981, was employed in the chemical industry in different positions, from plant engineer up to a manager at a factory for production of low density polyethylene. Since 1981, up to his retirement, he was employed at the university in Serbia and is a regular professor of production and processing of polymer materials, as the case, the methodology of scientific research work. And he worked on the petroleum, petrochemical and polymer industry in Serbia. He's published 105 articles and 172 reports, of which 60 articles, 57 reports were dedicated to Boscovich and his theory. So he's applying Boscovich's theory in his country to the chemical industry out there. So a few points. Boscovich is famous in his homeland, and there's an institute of Boscovich in Zagreb. He's just not very well publicised outside his homeland. If you look at scientists like Newton, England has a publicity campaign about him, Einstein has a publicity campaign, Maxwell probably has Scotland publicising him, but Boscovich never had much publicity. Ideally, there should have been bigger publicity for Boscovich after Rutherford experiment decided matter was made of point particles in mostly empty space, because that is basically Boscovich's theory. I'm quoting now from the Chemical Education Division's group. When he published the results of these experiments in 1911, Rutherford proposed a model for the structure of the atom that is still accepted today. He concluded that all the positive charge, and essentially all of the mass of the atom, is concentrated in an infinitesimally small fraction of the total volume of the atom, which he called the nucleus, from the Latin for the nut, nut. In other words, matter is concentrated in small regions of space as if it were points, i.e. point particle theory of Boscovich. There are various theories of matter, such as matter was continuous, but Boscovich's point particle is one being confirmed, but seems to have been a diversion of too much excitement over Einstein to notice that this revolution of Boscovich happened. William Whiteman says it is doubtful whether the reputation of any other natural philosopher at the first rank has suffered as much undeserved eclipse as that of Roger Boscovich, nor is the word eclipse an idle metaphor, for less than 50 years ago this luminary shone with a light undiminished by passage of a century. So in 1962, that's a quote from 1962, so he was mostly forgotten then for 50 years, and since then he's still mostly forgotten. Hermann Stoiljkovich it's generally accepted that the macro-molecular hypothesis was presented for the first time by Hermann. However, this is Dragoslav saying, when we would like to show that Roger Boscovich was the first one who announced macro-molecular hypothesis in his famous theory, Philosophy of Naturalness, as early as 1758. Boscovich held the matter to be discrete. The elemental particles of which matter is built were led to be the non-extended points. So the distance between these points is very large. There is an attractive force between them. With the decrease of distance, however, the repulsive force appears. rise, and then the attractive force appears again. This is the force curve showing that at very large distances the force is repulsive and prevents contact of the particles. Having in mind his force distance curve, Boscovich suggested that the atoms could be connected. And if we consider some details of what Boscovich is saying in his statements, we find that he's talking about this sort of structure, which is the ethylene molecule interaction presented by Leonard-Jones potential curve. And it's similar to what Boscovich's curve is talking about, published 1745. This is the Leonard-Jones potential curve, and that is also related to the curve that Boscovich gave us. So Boscovich pointed out that the spiral atomic chains could be formed. And according to Dragoslav, the priority of Boscovich's macromolecular hypothesis is unquestionable, and his theory is of some use as shown in the applications to modern polymer science, which is what Dragoslav wrote his papers about. Werner Heisenberg also talked about Boscovich, and he gave credit to Boscovich. So I reiterate this unified field theory from the 18th century. So I'm sort of running out of time, and on to part 3. I have another person dealing with Boscovich's theory, which was Augustus Prince. It's going by the extended version of the paper presented at the International Conference in 2011, which unfortunately is still published. His article is an analytical form for the Boscovich curve with applications. He's using an analysis from a physical and phenomenological viewpoint, employing the renowned and recognised continuity of Boscovich's force curve. He says further representations of force suggestions for the predictions of specific heat of solids, photoelectric effect, etc. The Boscovich points are assumed to move under the action of a force acceleration that varies inversely proportional to the curve to the cube or the radius from the point centre. So he analyses the Boscovich's force curve into 3 parts, part A, B and C, and gets this sort of mathematics. In region A, it's that equation. In region B, it's the other equation shown there, and in C, it's equation 64. Region A is the Newtonian range. Region B and the dark matter distance range as region C. The numerical values for the constants shown in that previous figure have been chosen to make the Boscovich curve continuous throughout. One must remember that the curve is a quantitative one and cannot be shown in scale due to the fact that in region A we measure distances in centimetres less, while in region B and C we measure distances in light years, and in region C we're speaking of millions of light years. And he's looked at it and found that there's a non-Planckian interpretation of black body radiation. In both cases, the agreement is with empirical data has been achieved. I also mentioned that this is a form of the equation would be used as an interpretation of the photoelectric effect, and this has been achieved, and the results address several concerns that have been raised about the linear assumption regarding frequency. So you have an extension of the photoelectric effect. My analysis confirms the idea that the equation is non-linear and may be described as being a function of frequency squared. this is talking about the photoelectric effect. There's more to the photoelectric effect than what Einstein was talking about. And we go to Millikan, and he was only making an approximation of having it as a linear equation. So in summary, Boscovich's theory tends to be ignored in university physics courses, and because there's too much emphasis on Einstein. Boscovich is known of in history of physics department, but has suffered for not being translated from Latin. Boscovich's idea is of a unified theory based on point particle. Point particle ideas is still used in modern physics. Some disciplines do reject the idea of point particle, but it is a natural progression of creation from a zero-dimensional entity into a three-dimensional entity, which is what we've got. So Boscovich's theory still has modern applications, as those people are pointing out. Some people are still aware of it. And that's basically the conclusion.
Thank you, Roger. Any questions for Roger?
No. Overwhelmed.
I want to point out that modern physics has progressed beyond the point particle, because from scattering theory, people have received Nobel Prizes for showing that all elementary particles that have mass have finite size and interior structure. For instance, the proton and neutron have 3 substructures. And that's why in the standard model of elementary particles, they build these particles out of quarks, 3 quarks, because they can actually see and observe that structure. So the point particle model is known to be an idealization.
Yeah, it's an idealization, but from the point particle, you are building up the other particles. So it's a building process. It's not, with Boscovich, there are macro particles.
Right. But
so it's building up from a point particle.
It turns out that quarks also have structure.
Yeah.
I'd like to point out that particles are ubiquitous throughout the universe, and Feynman believed that everything was particles rather than waves, because he could see the particles being measured. You could, if you looked at a screen, in sufficient detail, you could see the particles of photons hitting the screen. So the question of what particles are is still unknown, and it's a big mystery, because how can you understand a universe just made of particles?
This is what probably the understanding difficulty is. After Newton, it was what was matter made of, and Boscovich's theory is that it's point particles.
Yeah.
And Rutherford's experiments are supposed to have confirmed that it is matter is concentrated in points. So it's really a confirmation of what you're saying.
Yes,
but carrying on from point particles, you then build up other particles. Yeah. So from a 0 dimension, you then go to 1 dimension, to 2, 3, and so on. You do build it up from what point particles.
So we haven't really progressed greatly from Boscovich's ideas, I think.
Not really. You still treat particles.
Time for one more quick question.
I've heard you speak many times on this theory, so my question is not on your presentation per se, but just out of curiosity, did you make this whole trip primarily for this conference?
Yeah, mainly.
Thank you.
Trying to promote Boscovich's theory and people to work on it.
We all did. You know.
We all did, but except that
Except
mine
for
is
guys like this who just walked across campus.
Is there a Boscovich equation?
See?
How mathematical was Boscovich?
It was Augustus Prince who was working out the equations for it, and those are the equations for the curve, which is so complex.
This is what he did, yeah,
Yeah.
20 years ago or so.
20.
10 years ago, 20 years. But then Boscovich himself, he had a mathematical representation of his theory. Did he calculate anything?
Boscovich has a lot of mathematics, and he does. It's the start really of infinitesimal calculus. So Newton, when he wrote his books, invented calculus, and so Boscovich was picking up on calculus as well. So he did write a lot of mathematics. It just hasn't come through. So he's got, Boscovich has worked out this curve where you've got an attractive force and a repulsive force. So if the two particles that come together are attractive for a while, but then the repulsive force gets stronger and they get pushed apart. So he did work out the outline of all this maths.
Thank you again, Roger.